In this video, again, we're going to integrate and we're going to use partial fractions to help us simplify our integrand. But in this situation, we have a non-linear, not reducible factor. So we have a quadratic factor. And what we have said before is that everything needs to be linear. We want this denominator to be a product of linear factors. So we're going to look at how we can decompose the partial fractions when this nonlinear irreducible factor occurs. So before I even touch the integration, I am going to look at decomposing this into a sum of partial fractions. We're going to have three partial fractions here. So I've got x squared plus 1 and then x minus 1 squared. We are also dealing with a repeated factor. So this changes how we're going to write our answer. So my first factor, normally I would put an a here, but because this is quadratic, I'm going to write ax plus b, and that is a linear equation type 4. So I have ax plus b over x squared plus 1. And then we'll have plus c over my other factor, x minus 1. And because this x minus 1 is repeated, I'm then going to have d over x minus 1 squared. So take a minute, make sure you understand how I've set this up. Once we understand and we get the setup for how we deal with this quadratic factor, having a linear expression in the numerator as opposed to a linear having a constant in the numerator. So now we're going to multiply by the LCD, which is of course our original denominator, to clear the fractions. And once I've done that, I multiply by my LCD, which is x squared plus 1 times the quantity x minus 1 squared. We are left with 2x plus 4 equals ax plus b. That would be multiplied by x minus 1 squared plus c times x squared plus 1, x minus 1, plus d times x squared plus 1. So multiplying by the LCD to clear the fractions gives us this expression. Now I'm going to look at foiling all of this out, and specifically this first term. We're going to FOIL that and get something quadratic, and then we will multiply the ax plus b through. So I'm going to do a lot of distribution. This is going to look really long, and it may not fit all on one line. So once we do that, what we'll have, I'm going to leave my negative 2x plus 4. If I am to multiply all of this out, oh, it looks like I must have smudged out that x with my finger. If I multiply all of this out, that will leave me with ax cubed minus 2ax squared plus ax plus bx squared minus 2bx plus b. So that was multiplying out those three linear factors. The second piece, I'll then have plus c x cubed minus cx squared plus cx minus c. And then my third piece, that's basic distribution. I have plus dx squared plus d. You guys should have no problem multiplying and getting all of these terms. It is a little labor intensive, but it shouldn't be difficult per se. So now I'm going to match up my cubic terms, my quadratic terms, I have 4 of those, my linear terms, and my constant terms. I have 3 linear, 3 constant, and 2 cubic. And we're going to do this to help us set up a system of equations. So another way you might think about writing this is we'll say x cubed. My constant x cubed, I do not have a constant x cubed. I have 0 x cubed. How many x cubes do I have over here? I have 2. I've got cx cubed and ax cubed. So 0 equals a plus c. X squared. Again, I don't have an x squared coefficient on the left side, so I'll have 0 equals, and then we'll write the coefficients of my 3x squared, my 4x squared terms. I've got negative 2a, b, negative c, and d. So negative 2a plus b minus c and plus d. Those are my x squareds. For my linear, I have negative 2. So negative 2 equals, and I'm going to write my linear coefficients, positive a, negative 2b, and positive c. So I have a minus 2b plus c, and then my constant, I'll put a C for constant, is 4. And my constant coefficients are B, positive B, minus C, and D. B minus C plus D. So I'm going to organize this now that I've set up what my system of equations will be, which is this. I'm going to organize this into my matrix so I can do my row reduction. In the first video, I talk about using a matrix, and if you need extra help using the matrix on your TI calculator to solve the system, please email me and I will send you something that will walk you through it. All right, so in this situation, I'm going to set my matrix up, and we're going to think about this as having A, B, C, D. We'll have our bar for our augmented matrix, and then a constant. Okay, so A, I have 1A, 0B, 1C, and 0D. That would be equal to 0. My second row, negative 2A, 1B, negative 1C, and 1D equal to 0. My third row, I have 1A, negative 2B, 1C, 0D equal to my constant, negative 2. And lastly, 0A, 1B, negative 1C, positive 1D equal to 4. Again, if I went through that quick, pause the video and see if you can match up all of the terms. In this situation, when we start talking about the size of our matrix, remember we always list them as row by column. We have 4 rows and 5 columns. This is a 4 by 5 matrix that we want to enter into the matrix, edit a matrix in our calculator, type in our 4 by 5 matrix, and then we're going to compute or calculate reduced row echelon form, or RREF, of whatever matrix we name this as. So if I go through that process and I find my reduced row echelon form for this matrix, what the output is 1, 0, 0, 0, 2, 0, 1, 0, 0, 1, 0, 0, 1, 0, negative 2, 0, 0, 0, 1, 1. So now remembering what variables our columns represent, I can see that 1A is equal to the value of 2. 1B equals the value of 1. 1C equals negative 2. And 1D equals positive 1. So that's going to allow me to decompose my original fraction, and then the integration will be very simple. So I'm going to skip to the next page and write out what we're dealing with. So the fraction that we started with as our integrand is written here. And we said we were going to decompose it to look like ax plus b over x squared plus 1 plus c over x minus 1 plus d over x minus 1 quantity squared. Now, we found on our previous slide our a, b, and c values. We said that a is 2, b is 1, c is -2, and d is +1. So that means we're left with integrating 2x plus 1 over x squared plus 1 minus 2 over x minus 1 plus 1 over x minus 1 quantity squared. So now, the integral of a sum is the sum of the integrals. I'm going to look at breaking these apart. I have 3 fractions here. And this first fraction, 2x plus 1 over x squared plus 1, I can unadd that, and I can say 2x over x squared plus 1 over x squared plus 1. So what I'm dealing with is I have 2 of the integral of x over x squared plus 1 dx plus the integral 1 over x squared plus 1 dx minus 2 of the integral 1 over x minus 1 plus the integral of 1 over x minus 1 quantity squared. And I left my little dx out there. So now we have 4 basic small rational expressions to integrate. 1, 3, and 4, the first, third, and fourth one, are very easy to use a u substitution to solve. So as I said, in order to integrate this, we're going to use a u sub, and a u sub. The second one here, that is from our table of integrals. So we have a formula we can use to give us that answer. So my first piece, I would say let u equal x squared plus 1 du equals 2x dx. So this integral that we'll be doing is going to be the integral, and I really didn't need to pull that 2 out in front because there's my 2x. I've got 1 over u du. That would be my substitution, which of course is going to give me the natural log of the absolute value of u when I integrate, plus c. Second integral here is from our table. That's going to be tangent inverse of x. My third integral, I would say let u equal x minus 1, du equals dx. We're dealing with the integral of 1 over u du, which of course is going to again give us natural log of u. And the last one, let u equal x minus 1, du equals dx. That means we're dealing with the integral of 1 over u squared, which is the same as the integral of u to the -2, which would give us -1 u to the -1, or -1 over u. So my answer here, my first term is the natural log of u. My u substitution on that first was x squared plus 1. My second term is tangent inverse of x. My third term, I have minus 2 of that. I didn't have to include the 2 on the first term because that was factored in with my u substitution, but here I've got minus 2 of the natural log of u. My u in this case was x minus 1. And then I've got minus 1 over, my u value here was x minus 1 again. And of course, we end this with a plus c. So this is my final answer, and this is how I deal with integrating something that has to be broken down by partial fractions, but we have a non-reducible, non-linear factor in the denominator. As always, email me if you have any questions.